I'm not hearing anything. Well, good afternoon. Pleasure to be here today to talk to you all about what we know of vegetated cover and turf reinforcement mats. TRMs, as they're known, have been around for some time, but in the last several years, we've been able to put a number of the pieces of the puzzle together, which has been very instrumental, I believe, in allowing us to use TRMs as a real engineering tool. So the contents of what I wanted to talk about today. Little bit of overview of TRMs, where we're seeing them used, talk about channel flow testing, some new work we've done on anchor tests, some unsteady wave overtopping work that has been done all in the last decade here that's actually really taught us a lot about the performance of these systems and also the importance of the turf properties. Turf reinforcement mats, it comes to fathom that the turf part is actually important, and we've begun to develop ways to actually quantify that. What we know, of course, about turf mats is the idea is to provide an extra boundary layer, if you will, between the vegetation, the flow on top of vegetation, and the soil below, and enhance the root structure that is present in different types of vegetation and in different types of soil conditions, both of which are very important to the overall design. So in practice, green engineering, the idea, of course, is to be able to get more environmentally friendly procedures and tools in our box that we're able to apply to different applications where appropriate to enhance the environmental aesthetics and performance of engineered systems. Historically, we've seen turf mats being used in pond bank protection, wave run-up. I'll talk a little bit about that here in a minute, but lapping waves to protect shorelines. Channel protection. You see a lot of urbanized areas. As we get more and more people, we have to control that stormwater and be able to safely and effectively convey it to its downstream source. And with different types of vegetation. You can see we have area here where the channel was constructed and formed, low flow channel in the bottom, and then native vegetation allowed to establish and provide the supplemental protection over the TRM for these type of channelized environments. Stream bank restoration, a lot of areas, this is on a channel bend, as you can see the sloughing at the toe, rock was put in to try to stabilize that. Could talk a long time about rock, the pros and cons of different types of rock sizing equations, but the point would be to try to put nature back into the equation and put a system in place that was able to hold a slope behind it. You can see in conjunction with rock, I'll talk about the importance of different types of systems in a minute. But in conjunction with something below that ordinary water line that the vegetation can grow to and provide that interface between saturated conditions and areas where vegetation can actually establish. Slope stabilization, you can see here on the left an area where there's a typical sloughing failure, probably a pop out, saturation within the bank, stress along the toe of the embankment, and you have a geotechnical stability issue that turf reinforcement mats, a lot of times with the presence of anchors, again, which we'll touch on, can be brought in, regrade that system, regrade that section, and install vegetation to be able to provide the stability here downstream of this structure. Steep slope stabilization is really a geotechnical issue. Of course, there's some hydraulic component with that. Typically, it's just with rain runoff. But the idea, again, is to be able to use the tensile properties and the strength of a TRM in conjunction with anchors in many cases to provide that enhanced stability on steep slopes and prevent the toe, as you see here on the left, getting washed out or pushed out, as most commonly is the case because of poor water pressure within the embankment itself. Dam embankment protection. You can see here on the left an area where this dam was overtopped and destroyed the vegetation area just downstream of the rock protection. We're able to come in, put a TRM in there to be able to effectively protect that area from subsequent overtopping of that facility. A lot of the testing that we've done has been in this environment, in a very steep gradient, high energy, supercritical flow environment. So we're becoming much more confident with the application of TRMs in this type of environment. Levee overtopping protection, the idea is to be able to protect the back side of the levees, as you can see here on the left, and then a close-up on the right side of the picture. Talk a good bit about this because we've had the fortunate conditions of being able to do an awful lot of testing on different types of TRMs, different types of vegetations, different types of soils to be able to put together, I won't say a design procedure, but the beginnings of a design methodology to allow us as engineers and owners and specifiers to be able to employ these technologies where appropriate. And as I said before, combined solution. There's never one tool in our box that's really suited for everything. So the trick is to be able to pick the proper tool. You can see we have ACBs in an area right downstream of an outlet rock where the ordinary high water would come up to, and then a TRM on the side slope of this channel to be able to provide vegetated protection in conjunction with the other components of this system that were developed to provide stability in this area. So the idea of the turf reinforcement is, of course, to improve the native vegetation. We want to work with nature and provide a protection from hydraulic and non-hydraulic forces that will ensure the longevity of a project and the viability of the engineered solution. Problem that we have with vegetation is, even going back to the Hewlett curves, which we'll talk about here in a minute, it's very complex. It's not a simple rock sizing equation or a block technology where it's a free body diagram of a single particle. We have a lot of interaction between the specific vegetation, the soil type, the type of TRM, the inherent properties of that turf reinforcement mat itself, and the growing seasons. What part of the country is the project in will really dictate what is the native vegetation and how appropriate would a vegetated system be in any given environment. So we know that there's two main types of properties to be evaluated with TRMs. One is index properties, which are used to identify products: tensile strength, thickness, light penetration, elongation, UV stabilization, mass per unit area, a number of quantifiable aspects of each individual tool that can be used certainly for comparison, but we also hope for some prediction of performance, overall longevity of the system and system performance, which relates to the hydraulic performance properties, which I talk mainly about today. But we need to be able to quantify the use of each of the different types of products in coordination with their significant parameters, which would be typically velocity and shear stress, both in an unvegetated and a vegetated condition. So index properties are important, of course, for the use. You can see here on the left, we have a site that was used as a haul road along this levee so that they could bring the concrete trucks in and pour this T-wall that was put in place to dissipate the energy of splash over this wall. The water would come across and go down the protected side. This area was driven on with concrete trucks, and you can see the vegetation was disturbed there where the traffic was, but the mat is still in place. Conversely, have an area here, again, same type of T-wall, concrete pad up at the top. Mowers caught it. So just because the maintenance at this site caused catastrophic, I'd say, damage to the system, and now we have much less protection than was actually designed for or hoped with the stability of this entire levee. So the index properties are extremely important to the overall design and viability. Have to think about maintenance, the installation, how are you going to get the product on the ground, what type of maintenance activity will be happening on the site. Wildlife impacts, whether it be burrowing, as you can see here on the left, small animals burrowing in. Below this, the red dashed line is where the TRM is, and above it, there's no TRM, and you can see sort of where the burrowing just stopped right at that interface of the TRM. Habitat, critters being stuck in the mats is a concern in a lot of areas. So the actual makeup and index properties of the TRM is important to ensure that whatever native species are there or types of wildlife interaction is not detrimental to the wildlife or to the system itself. And good old hogs, feral hogs. This study was done down in Mississippi or in Louisiana, I'm sorry, to investigate the strength of materials, buried garbage literally underneath the mats, and videoed then over the course of several weeks what would be destroyed and what wouldn't, and we're able to correlate the effort that the hogs would take to dig something up back to the performance properties, index properties of the TRM itself. Debris loading is very important. You can see on the left side a levee that's been overtopped, and the debris that was washed over that certainly had an effect of losing some vegetation, but the TRM is still intact and still in place. Contrast to the picture on the right, and we can see where this tree root, you could almost recreate the bouncing of that root as it came down this channel and destroyed the protective cover that was put in place. Any flow now that would wash across that system would get underneath the TRM and cause significant damage to the soil underlaying the system. So the strength of that TRM is extremely important, mainly before the vegetation is able to take hold. UV exposure is very important. You can see the map on the left of high UV areas in the United States. So a geographic area of a project is one of the key components that we have to investigate when we're actually designing, is to know what sort of vegetation and sunlight exposure we expect to have. You can see on the right side here the degradation just because of sun. So UV exposure is a key component in determining the strength of a TRM, certainly with its mechanical connection capabilities, but most importantly with its what we call functional longevity. The idea is, how long will it last? What's the design life of a TRM system? And we're not quite there yet. ASTM's been working very diligently to be able to define what functional longevity actually means, and we'd like to have an opportunity to share a lot of what we know about the index properties and the importance of those index properties in a future webinar. So stay tuned for that one. We're hoping to have that here in December to talk about the non-hydraulic stresses and forces associated with TRMs. But today, really want to focus on the hydraulic conditions. Here at Colorado State University, we've been fortunate enough to do, last 2.5 decades probably, a lot of the testing that's been done on TRMs. Other institutions, TRI has been huge in providing data that we're able to pull together and understand what's happening to these systems and how can we best use them? How can we best provide tools for people to be able to employ for erosion control and stabilization techniques? So I'll start with channel flow testing. We really want to understand the limits of performance. What's the critical shear stress? What's the critical velocity? My soapbox right now is stream power. I think it's a combination of shear stress and velocity that we have to investigate. But we want to be able to know in an unvegetated condition. So as soon as the product gets put on the ground, you really cross your fingers that you don't get your design event until your vegetation establishes, right? It takes a little bit to get veg to establish. So we have to have some idea of, in an unvegetated condition, what's the performance, and then certainly in a fully vegetated condition, as you can see here in this picture below, what the performance would be. This picture is probably not indicative of 90% of the installations because this is supercritical flow. This is a steep channel, high velocity going through here. It is how we test these systems, however, so that we ensure that the performance values we get in high energy conditions are certainly able to be interpolated down to lower energy subcritical conditions. Going the other way, we know from a lot of work that's been done in energy dissipation that testing in a subcritical application and applying to a high energy supercritical application is not at all conservative. So the way we do this at Colorado State is the unvegetated testing. We have several flumes. This one's 2 feet wide. We have one that's 4 feet wide and one that's 6 feet wide. You can see this is supercritical flow here on the left. So you put the product in per the manufacturer's recommendation, installation recommendations, and then we can adjust slope and discharge to target different values of shear stress and velocity. At the end of each test, you can see the pins that are marked there with the red paint. You go through and survey the entire bed so that you can have a quantification then of what soil has been lost within that specific system. Typical ranges per ASTM D6460, channelized testing range from 5 to 15 feet per second in an unvegetated condition, and shears 1 to 5 pounds per square foot. Manning's N is important. What we've seen is across the different types of TRMs, between 0.02 and 0.35 for unvegetated conditions, certainly much higher for vegetated, for freeboard calculations. Certainly you need to know for velocity, but it's really a freeboard calc that you need that Manning's N for so that you have an idea of how deep the water is going to be in your design channel. The results of the unvegetated testing look a lot like this. The idea is to be able to determine your soil loss through either LiDAR scanning, which we'll talk about in a second, or just point gauge volume calculations, and then a permissible shear stress. And what we see for almost every type of system we've looked at is a curve similar to this, where it's not a perfect fit because nature has a way of throwing a curve, no pun intended, into everything. But we're able to see a pretty good correlation between increasing shear stress and increasing soil loss. The value in industry standard right now is a half an inch of soil loss, with the thought being once you get a half an inch of soil loss in an unvegetated condition, you no longer have a viable seabed. So anything up until that half inch, your material's just sort of resorting and moving around. But once you get past that half inch soil loss, you've lost the ability for vegetation to then establish through the mat into the soil and provide long-term protection. So this plot shows shear stress, certainly a same type of situation with velocity. As I said, ASTM really calls out shear stress right now. Personally, I always look at both. Physics is physics, and so the lift and drag are probably equally important. So you want to be able to quantify, as we have here, the effect of velocity on that soil loss also. What it means to designers is at the end of the day, we have plots that look like this. So for different types of TRMs, doesn't matter whose they are here, 1 and 2, you can see we have a bare soil line, this black line. Lose soil pretty quickly as a function of shear stress, and then 2 different TRMs. So permits the designer, specifier, engineer to look at a variety of different techniques and select the one that is certainly the best performing for the application that they have, and then be able to do the cost-benefit analysis of what would be the most appropriate system. Realizing that this is in an unvegetated condition, so it's sort of right out of the gate. As soon as the mat's put down on the ground, what performance do I expect? Realizing that I'm going to tend towards a vegetated performance value. It takes a lot longer to do these tests. You can see the planter box here on the left-hand side. They're 40 feet long, 4 feet wide, able to grow different vegetations in different soil types, different TRMs, and then we put them in a steep flume, lift them up with a crane, 2-to-1 slope, 100 feet long, that we're able to get very high velocities and very high shear stresses. The importance, of course, is being able to quantify what's the soil type. The soil, as we've learned from a lot of the wave overtopping tests, is very important. So determining performance across varying soil types is paramount to the portfolio of design tools that we have available to us. The type of mat, the stapling pattern, the vegetation that's established, these were some of the early trays that we put through the testing regimen here at CSU, and hindsight being 2020, we realized very quickly that this was like a smorgasbord for the deer. It was a perfect height for them to come in and just have lunch. So we had to put covers over them to get the vegetation to establish and then grow it. So we looked at a number of different growing seasons, different densities of vegetation, realizing that nature isn't as kind as graduate students in a laboratory to be able to get a perfect stand of vegetation. So being able to back up and quantify performance as a function of the vegetative and soil parameters has been important for the understanding of how these systems work. Once we've reached a vegetation quality and density that is commensurate with what the specific manufacturer is looking to do, we pick it up, put it in the flume, and run a series of discharges over it. It's just like with the unvegetated tests, they typically run for 35 to 40 minutes to be able to see quantify what's happening at each stress level. So we set a discharge, students take water surface elevations that we run through an algorithm that was actually developed for articulated block, but it works for any type of supercritical flow. It's an ASTM standard also, to be able to interpret then the data and determine in a vegetated state what sort of permissible velocities and shear stresses we're able to obtain. Historically, we found with the 2 growing seasons of pyramid, I'm allowed to say upwards of 30 feet per second, 15 to 30 feet per second across the range of TRMs, and upwards of 20 pounds of shear stress, which is a tremendous load. That's a lot of force that's being imparted and absorbed by the TRM. The vegetation's doing part, the TRM's doing part, and the interaction then of all 3 components, veg, TRM, and soil, make up the last third of it. Roughnesses with the vegetated system, of course, will depend some on height of vegetation and density, but typically that 022 to 045 range is what we found over the course of the couple dozen tests that we've done in a vegetated condition. Just recently, we've investigated the importance in the use of anchors with TRMs. I've understood for some time that anchors could be incorporated, as you see here on the left, through different knowing what the soil strata is at a site for different depths to get geotechnical stability, and it was always assumed hydraulic stability. However, that had never really been quantified. You can see here on the right an anchor head that's holding the TRM down, and a little bit of the spacing. I'll talk about that in a second. As I said, the geotechnical benefits pretty well understood. There's a lot of empirical relationships and software packages that will allow us to determine what that failure cone is going to be, the depth of anchor, the spacing of anchor, and how geotechnically, as I said, with steep slopes or even with channel restoration for pop out and saturation failures, how to sandwich those layers together to ensure the geotechnical stability. The hydraulic benefit of it, though, has sort of been assumed. We haven't really, up until the last several months, had the opportunity to isolate the anchor itself and the combination of anchor, TRM, spacing, and hydraulic load in the overall performance of a TRM system. You can see here this is a rather steep slope around this bend. So the anchors are asked to do two things. They're asked to hold the slope in place geotechnically and then provide hydraulic stability as the velocity accelerates around this corner. Important to notice, again, used with another form of protection here at the toe so that you're holding the toe in place and providing vegetated protection up above it. So the way we did this was in a 6-foot wide flume here at the university. We did a series of three system tests. First was bare soil. The second was paramount TRM without any anchors. And the third was that same baseline paramount with anchors. So the idea was to have an understanding here. You can see on the left just a clay sand, very close to the ASTM specified soil for the D6460 tests. Ran a suite of discharges over it and quantified erosion. Put just the TRM with the pin spacing that is recommended per ProPEX, and then looked at anchor testing. So we realized quickly that we weren't evaluating the geotechnical stability. What we wanted to evaluate was the hydraulic performance of the anchors. So we tethered the anchors to the bottom of the channel just with cables, and then put them in the spacing again that was most indicative of what we saw for field installations. So not too tight, not too loose, as Mama Bear says, just right, to have a spacing of those anchors. And one of the things we wanted to know is, does that spacing have an effect on the performance of the system? So put the soil in, compacted it, put the TRM down, pinned. You can see the pins running down, and then the anchors in an offset pattern throughout the width of the flume and length of the flume. Again, this is 6 feet wide and about 35 feet long. The idea then was to do just like we did in the unvegetated tests, as I showed previously, to look at a combination of slope. This is a tilting bed flume, so we can go from horizontal to about 25% slope, discharges up to about 40 cubic feet per second. Supercritical flow to be able to quantify the water surface. ASTM D7276 is the standard that interpretation standard that we use for supercritical flow analysis, so that you back out a roughness based on your discharge slope, geometry, and measured water surface elevation. So it was important for the guys to go through with a point gauge and very carefully, accurately get the water surface throughout this test reach. Three locations across the channel and every 2 feet down the length, so that we could rebuild that hydraulic model and determine what the stresses were. Before we made correlations, though, we had to document the soil loss. So you can see typically what we've done in the past is with a point gauge, you go through and try to find the gully and then measure the depth of that gully and then hope you can sort of back that into some average soil loss across your system or representative value of soil loss per given shear stress in correlation to what that half-inch threshold would be. What we've gone to now, though, is LiDAR scanning. I can see the LiDAR instrument here on the right, able to scan it before we do a test, and then at the end of the last test, when we realize that there is gullying, we're able to pull the product up, put the LiDAR back in, and rescan it. That gives us a very detailed representation of depth and location of soil loss, so that we can then look at contour maps and be able to understand a little better how is the soil trying to move through the system, or how is it being eroded out from underneath the mats. For the purpose of this set of runs, looked at 6 different discharges across a couple of different slopes to be able to generate shear stresses and velocities from about 4 feet per second up to 9 feet per second, and shear stresses just over a half a pound up to 3 pounds of shear. So within the range of what we were seeing for other unvegetated tests, but the importance was the comparison. We wanted to have a set of tests, these same runs on bare soil, unanchored pyramid, and anchored pyramid, and then be able to relate that back to the soil loss. So once we took the LiDAR, we were able to look at gains. The red area is where material was deposited, typically behind pins and behind anchors. You can see one of the real benefits hydraulically to the anchors is it stops the bed forms from trying to move through a channel. So it pushes the shear stress up on top of the mat instead of letting the shear stress that's underneath the mat push material through. So those anchors actually work as little dams to help back up water, stop that velocity, slow that velocity down right upstream of the anchor, thus restricting movement. So for the same flow condition, we can see areas of loss with an unanchored system and then actual areas of mounding of soil with the anchored system. So to compare these now, I wanted to know, couldn't we quantify what the effect of the anchor is? So for each run with the ArmorMax system and the Paramat, you can see ArmorMax in blue, Paramat in orange, the soil loss. It was considerably less soil loss for the same flow condition with the anchors and without the anchors. Wanted to then put that back into context of shear stress. And again, we're able to see soil loss on the x-axis and shear stress on the y-axis. And what's interesting about this is the different zones we have of slopes of lines. And we're still working on this, to be determined what the actual methodology that will come out of this, but we're seeing sort of a healing process, if you will. You can see in the green line and even on the red, you get some soil movement pretty quickly and then it sort of flattens out. And then you get some soil movement and then it begins to flatten out. So that process of the sine curve essentially associated with soil loss is directly related to the bed form functions that we know exist. But functionally for design, we want to understand sort of the bins that we're in for shear stress and how can we best pick a product knowing what that initial event might be before our vegetation gets established. So while I didn't put equations on this to bore you with numbers, it's the slope of these lines comparing across different anchored and not anchored that are important, and the flattening of the slope of the anchored system shows that those anchors are really retarding the speed at which material is able to be eroded out from underneath a TRM system. Now, we only have a few data points, but of course the idea then is to be able to evaluate the percent improvement, essentially, of anchors. And we're seeing conservatively, we saw upwards of 500% improvement in some of these tests, but we're able to make plots now of the red line with the anchored system and the green line with the unanchored Paramat considerable. About, here just to pick a spot here for a clay loam, almost 100% increase in shear stress for the same soil loss conditions. So it told us that the benefits of the anchors, not only for geotechnical stability, but also for the hydraulic stability, are huge. And something that it's been the first time we've been able to actually quantify that and turn it into some sort of design recommendation with the hopes being able to develop a design methodology here in the future for incorporating anchors. I want to talk some now about the unsteady testing. It's the same idea. It's a hydraulic load, but it's a function of time. Unsteady wave overtopping, of course, a wave comes over the top of an embankment, then it's still, then a wave, then it's still. So it's that dynamic loading. There's an impact, there's a centripetal acceleration because of change in geometry and change in volume of each individual wave, but it's a very different environment, much more harsh, much more hydraulically powerful than a steady state condition. Waves aren't just on the coast though either. We know that inland ponds, you can see this function here of wave height versus fetch in miles, and you can get significant waves. The different colors are different wind speeds, but even with a 1 mile wind fetch, meaning direction that the wind could travel before it hits the protection, is considerable. You can get up over a foot wave, and then you have a longer fetch, you can get up to 5 foot waves. So that's a very significant stress to be putting on the system. This is an application that could experience that type of environment where you have a long fetch length here approaching the embankment. The wave would come over the top and accelerate down this back protected side of the system. Levees, of course, are coastal, so you have much higher waves, much higher periods, frequencies of those waves, and a lot more stress. So it was really important for the Corps of Engineers to understand how these types of products and technologies would work in this unsteady, high-energy overtopping environment. We know pretty well the overtopping, the mechanics of overtopping, if you will. The hindcasters and the coastal engineers for decades now have been able to develop distribution volume curves for overtopping flow characteristics for different storm conditions. Just like a channel, every location is different as to the type of stress that we'd see. But what we don't know is what we didn't know was the correlation between the unsteady hydraulic loading and steady state hydraulic loading, the effect of the species, the coverage, the effect of soil types on it, and then what sort of strength could we quantify? What sort of improvement can we quantify for using TRMs in this high energy, highly turbulent environment? So as I said, the mechanics are pretty well understood. For any given storm condition, you can see here on the left, across the face of a levee, the crest of a levee, there's a signature velocity and depth. It's totally a function of what the storm is and what the geometry of that levee is. Well, the Dutch were instrumental in developing a device that would allow them to simulate that depth and velocity on the top of a levee. Picture up here in the upper right is Dr. Van der Meer's mobile simulator, that allowed him to go to different sites in the Netherlands and actually test this theory out and develop the method that we could use to bring storms to a grassed system. Colorado, this is what it looks like. We have our simulator up on the crest here that is computer controlled to be able to form whatever size and frequency distribution of waves a given storm for a given geographic location would produce. Have two sets of trays here. So the idea was to have the simulator up on top and then grow trays with different vegetations, different soil types, different protection schemes, and bring them into the facility. The trays were built in two sections, so a typical levee, a 3-to-1 slope, and then transitioned into a 25-to-1 slope. Berm was extremely important because, as I said about change in direction, the centripetal acceleration from the 3-to-1 to the 25-to-1 is about a factor of 3. So the velocity and shear stress increase from what you would determine on a steady slope by about 3 times just at that point of inflection. So the geometry of the levees that were tested was extremely important. Worked with Dr. Beasley out of LSU. He was our plant expert. Again, different materials. This is a sand material from Jacksonville that we brought in, sod that was grown in that region. Brought them into the greenhouses, about 10,000 square feet of climate-controlled greenhouse, to be able to grow the vegetation as it would in the field, either in Louisiana or in Jacksonville, Central Florida. Trays were then brought into the flume, picked up with a crane, put in so that we, again, brought the levee to the simulator to be able to evaluate different types of conditions. We've done an awful lot of tests on these. We had 11 tests with TRMs, ACBs, bare clay, lime stabilized clay, different densities, different strengths of vegetation, native vegetation. Looked at 4 different soil types, 2 different TRMs on sandy soils, again with different grass densities on the different soil conditions. Did a test for Propex on a seed system. These were all done with sod. They assume that that's how they would install them in the field, but we've looked at seeded systems, which I'll show in a couple minutes here, and then did a series of tests that there were 5 different TRMs that were brought to us to be able to evaluate under the New Orleans clay and a Bermuda sod to be able to really isolate the effect of the index properties essentially on the performance of these TRMs. A lot of different tests. The purpose of this slide, a lot of different overtopping rates. Interest of time, I won't get into the details of these, but very low flow conditions, this 0.02 CFS per foot, this number is just really a surrogate for the volume of water. How big is the wave? 4 CFS per foot, that's a big wave. So you have a lot of water coming over the top. Dormant grass, so what happens if you get your storm while your grass is in the middle of its dormant season, and then again, all the different performance techniques or protection techniques that were evaluated. So just a few pictures real quick. The bare soil tests, you can see down here at the break of slope is where everything started to happen, and the gullies worked themselves upstream. In the bare clay, after about an hour at 0.012 CFS per foot, which is very low overtopping, we had a lot of damage, and then total failure 20 minutes into 0.2 CFS per foot. With the grass then on the slope, took some core samples here and plugged them. We can see it's a little harder to quantify at the very beginning, so we had to very carefully go in, and you couldn't really LiDAR this, so we had to use our survey equipment to take our survey data, but you can sort of see the wet areas here as to where those gullies have formed. So water's beginning to channelize within this grassed tray, and that channelization would only continue then from this downstream point. This is at that break and slope and work its way upstream. So rather significant 2 CFS per foot at the end of 3 hours, rather significant damage and erosion to that system. Next was to look at what I call a tight weave TRM. I'll talk about that more in a second, but a very low light penetration value on it. You can see a little bit of the TRM starting to poke through here, but after the third test of 4 hours each at 4 CFS per foot, the embankment was still in very, very good shape. So in contrast to 2 CF, half that load, at the end of 2 hours, we saw significant damage. The presence of a TRM provided significant levels of performance increase to that vegetated system. More of an open weave TRM, again, at the very beginning, we were able to see beginnings of movement, and then the gullies start to form and work their way back up. So the quantification was important, and again, the way we did this was with our total station so that we could go through and actually map. It was a ridiculous number of points. You can see the outline here on the bed, but to be able to quantify now what that erosion would be so that we could find the hot spots, know where they formed, which was important for soil type, which I'll talk about in a second. But down here at the end of the break-in slope is where we saw the erosion start and then work its way up with the bare clay. And to be able to then turn that into a surrogate of performance. And the surrogate was cumulative overtopping volume. So we took these values of soil loss, and as a team, a Corps of Engineers, the research team here at CSU, and the consultants that were on board, what's appropriate and what isn't. We didn't have a threshold to say, okay, if half-inch soil loss, then you've lost your system. So we had to use sort of more of a qualitative assessment of what we thought was an appropriate level of performance, and then be consistent with that assessment throughout each of the techniques. So what that resulted in was a plot that showed no damage, significant damage for all the different techniques. The important part is down here at the bottom, where we have TRMs and no TRMs. What we found was that with an open weave TRM, meaning a light penetration that was very high, and grass by itself, there was no significant improvement, no real change in overtopping volume, the amount of water, the load essentially that could be put on that system. With a HPTRM, significantly different amount of volume was able to put over a longer period of time. So not only was it a higher stress, but it continued for a longer period of time, which told us that there was something there. There's something that we had to evaluate to understand why there was damage there, at significant damage at a lower open area and no damage at a tighter area. Before we were able to do that, we had another soil type. Again, the 4 different soils, sandy soils from Florida. Again, different coverages, different TRMs, different, again, soil conditions. Same type of surveying. The interesting thing here is you can see on the picture of the right that our damage wasn't down here at the toe of the slope, it was at the crest, much more dangerous. This head cut's going to work its way back up to the crest, and then you have a very different overtopping condition than what you've designed for. So with the sandy soils and the low volumes of overtopping associated with that, we saw our damage at the upper end of the slope, not down at the lower end of the slope. So grass only, you can see the damage that was starting to form. With a TRM, we were able to go through and quantify those same locations and that same relative performance value of the turf mat itself. Comparing all that, then we wanted to look at if we had our dormant, the black line here that says no damage, MVN is the clay that came from Louisiana, the overtopping volume that we were able to get. And then with a sandy soil for two different types of TRM, you can see the failure locations of each of those. So that the difference in the y-axis on this graph shows us the soil difference. So as you would expect, the combination of vegetation and soil have a dramatic effect on the performance. And we also saw a differential in performance in time and duration, or time and loading, across two different types of high performance TRM. So again, we wanted to be able to look at the grass failure by itself and then TRM failures across different types of hydraulic loading with two different types of TRMs and be able to understand why those were different. Which brings us into the importance of the turf properties. So this sort of goes together with some of the index properties, but they're tied together in some of the perceptions I'd like to touch on. Hewlett curves, you're familiar with those on good, normal, and poor types of vegetation and duration time and limiting velocity. Been around for a long, long time, sort of used in court. They're defensible in court. However, there's not a lot of good description on, do I have good, average, or poor grass? Good and poor are described by Hewlett, but average is sort of, well, if it's neither of these, it's average. So we had to start out by determining what is vegetation quality. 4 different pictures here. Each of us could have a different take on what that quality of vegetation would be. Again, we know from Hewlett the stiffness and the length, the surface area, the depth of the root structure, the density of the rhizomes and surface root structure are all very important, hadn't been quantified, and are very different for different types of vegetation and different types of soil types. So the idea was to be able to start with being able to walk out to a field site, assess these 4 pictures, and turn it into something that you could use as a quantifiable technique to develop a protection scheme. So the first was vegetated cover from the top down. Typically, you'd use a square in the past and count stems. We used to do that with the vegetated testing here. The students would count stems and stalks of vegetation in little 4 square centimeter boxes and then average that over the course of the embankment. Same idea here on the left. Just team was able to come up with a much better way to do that using digital photography, where they can go in and actually get a very reproducible, quantifiable determination of what that surface area or that surface coverage is. We realized quickly, though, that surface wasn't the main indicator. We could have very similar surface density values, but very different hydraulic performances. So we had to understand what was going on below the surface. And unless you have Jeff that's able to go out there and really see what's happening, we got to be able to start with some sort of quantifiable technique. So Jeff's team knew that there was difference in environment, difference in species. Management had a huge impact on what these root structures were going to look like. So we went out in the field and gathered hundreds of samples, just simple core samples that he was able to take back into the laboratory and do his root analysis. What that means is a very scientific investigation of as many of the performance parameters of roots that he could quantify. Excuse me, there was about 30 that he was able to run, 30 different parameters that he was able to determine with his testing. But we realized that the total root length, the surface area, the diameter, and the volume kept rising to the top of being the most important. You can see here as they come through the TRM into the material, that's what we had to know. We had to understand what was happening with those roots. So we started an exhaustive exercise in looking at correlations. I mean, it was really as a shot in the dark to begin with, and then we're able to see what was making sense and what was correlating well with other parameters related back to the hydraulics, and found that the root length times the root volume, which in hindsight makes a little bit of physical sense, was giving us a very, very strong correlation. I've termed this the Beasley number in recognition of all Jeff's work. He hates this, but it's sort of what stuck. But it's the root length times the root volume. So now we wanted to be able to correlate that back, as I said, to performance. So I'm going to go through these plots quickly, but they just tell a sort of a story. So the Beasley number for bare clay is 0, and you can see my cumulative overtopping volume, which is, again, is the surrogate for load that was put onto the embankment, about 5,500. If I have unreinforced grass, my core samples gave me a Beasley number of about 27,000, and I had a corresponding performance associated with that unreinforced Bermuda grass. I had a test, as I remember I said, that was on a very open TRM that was very similar to the unreinforced vegetation and performance. Its Beasley number was about the same, and its performance was about the same, which would, again, in hindsight, make sense. Put in the paramount product that we had, and the Beasley number was less, but the performance was 3 times greater. So we could put 3 times the load, stress, and duration on the same vegetation, same soil, because of the presence of the TRM over an unreinforced and a much open system. So that brought us right to the percent open area. How do those two correlate? So again, if we have 100% open, meaning no product there at all, again, our correlation, the vegetation again had 100% open area, bare clay, and then unreinforced Bermuda. The very open TRM, 95% open area, we guessed. Didn't have a cut sheet on that one. But then down into the 15% open area with the paramount. So we saw a strong correlation, albeit 2 points, 3, but between the open area and the overtopping load that could be put on that for a clay embankment. As I said earlier, we did a seeded test, so it was a different TRM with seed in it, so a little better than the bare clay itself, but the seed had just a couple of months to establish, and then a different TRM that had a higher or a lower light penetration, tighter weave TRM. So again, the difference in that performance for the same growing period with seed is a function of that percent open area of the TRM itself. Told us that we had a pretty strong correlation between that specific index property and performance. Sand tests, same idea, percent open area, 100% for the 4 different soil types that we had, the 35% open area TRM, and then a 15% open. So again, that correlation across sand, while the loading was lower because of the soil and vegetation makeup, the percent open area had that same direct correlation in performance. Beasley number was interesting with this one. So the Beasley number on bare sand was 0, as you can expect, doesn't take much flow. Different soil types, organic and inorganic, unreinforced material. The 35% open TRM had a Beasley number of just under 6,500. And then while we saw the tighter TRM with the sandy soil actually had a significantly higher Beasley number, higher performance and Beasley number, which was contrary to what has been thrown around the marketplace of, well, if it's too tight, you don't get vegetation to grow through it. It's a function of the soil parameter as to how long it takes that vegetation to get through the material itself. So through 2 types of vegetation, 2 types of TRM, and 2 types of soil material across a very different storm loading conditions, we're able to develop a bubble chart, if you will, where the size of the bubble is the Beasley number, and then the y-axis is overtopping volume as a function of that light penetration. We'll talk more about these index properties in the next webinar. but we're seeing very, very strong correlation between the percent open area of these TRMs and the ability of them to be able to provide protection in a very, very turbulent high energy condition, which per our design tools allow us to make that same interpolation back to more tranquil flow conditions. Just a quick video of, we had to pull, oops, well, there's video of trying to scrape this TRM off the slope. It absolutely didn't want to, there it goes, didn't want to come off. A track backhoe was trying to scrape it off so that we could reinstall it. The slope had to be changed. Couldn't get it to come up. Brought in a track hoe to be able to scrape it off, and that was taking forever. You can see the hourly rate that's going on here from the core folks watching that happen, and finally decided to hell with it. Let's bring in a D7 and just start D6. This is, and tear it up to get it off. So we're able to see even in the field that this interaction of the vegetation, the soil, and the engineered product was very, very effective in providing strong surface protection to that levee and to engineered solutions. So I know that was a lot in an hour of 2.5 decades worth of understanding of how these products work. Certainly would welcome the opportunity to ask any questions, answer any questions you may have.
Thanks, Chris. This is Drew Lawaza. I'm the Engineering Services Manager here at Propex. We've got a couple questions. As we go through these, if you have more, please type them in on the side there. We'll just go through one at a time. And Chris, if you can help me answer some of these questions, that'd be great.
You bet.
So the first question was, I believe this is related to the anchored hydraulic testing. The question is, did you actually measure the shear stress, or was it calculated as a function of velocity and slope?
Yeah, that's a great question. It was calculated as a function of the hydraulics. So it was not a direct measurement on top of or beneath the mat. The shear stress was determined by accurately quantifying the hydraulics of that flow condition.
Okay. Next question, I'll answer this one. Is it possible to get a PDF of the presentation? I believe this is all recorded and it will be online on the website after this the presentation is completed. Next question says, it seems that TRMs could be used with soil nails to reinforce the soil mass as well as providing surface protection. Soil nails are typically used with shotcrete facing, but TRMs might be a better and more cost effective application. Your thoughts? If you don't mind, I'll take this one. So we actually have a system. We talked about it, or Chris talked about it today, called ArmorMax. It's our paramount 75 along with engineered earth anchors. We focused on the hydraulic application today, but one of the main applications as well is for superficial slope stability for a geotechnical function. So to answer your question, yes, we definitely use a TRM with a soil nail type system for superficial stability, but really we're looking at using ArmorMax in that application. For that, we have anchors that we use to stabilize the slope depending on the design need. We also use a higher strength turf reinforcement mat, or a high performance turf reinforcement mat. And those applications, the combination of the two, the strength of the HPTRM and the capacity and spacing of the anchors are critical for that. So we definitely do a lot of work towards those applications. Additionally, we have done some combinations where we use ArmorMax along with soil nails. I can get you some more information on that if you have more questions. The next question is, let's see. It says, were there comparisons in establishing turf by seed below the TRM versus above the TRM? So yeah, I think this is more
early on we did that and found that the establishing the seed above was more effective than below.
Yeah, agreed. It's there's a difference in whether you're reinforcing the roots below or protecting the stems above.
That's right. Allowing it to grow from the top down really enhanced the stability of that root interface, root soil interface.
Yeah, agreed. Next question, any issues with irrigation sprinklers located within the mat? You can chime in, our experience is we have a lot of applications in areas where irrigation is used, irrigation systems. It's important to have a TRM that's dimensionally stable, something that when you cut into the material, it doesn't fry and fall apart. Pyramat 75 specifically does very well with that application. We have a lot of projects where irrigation systems are installed within the material, whether it's an irrigation system or an existing tree or shrub or any other type of mechanical connection or transition. A dimensionally stable product is critical. Next question was, do you have or do you look at any heavier TRMs other than Pyramat? I'm not any heavier TRMs other than Pyramat. If you can clarify, that'd be helpful.
I've evaluated a lot of them. I'm not able to speak specifically. I am able to answer any specific questions about Pyramat because they've authorized me to do that. But other manufacturers' test results, I can't speak to specifically.
And I would also, I'm a little biased, but I would argue that Pyramat's a pretty heavy TRM, one of the strongest out there. So if you can clarify, we can answer more directly. Next question is, how important is it to make sure the top of the TRM is properly entrenched into the bank?
Extremely.
Yes, agreed.
We'll
really for most every.
Go ahead. The next one, but well, I was just going to say, sorry, Drew. We'll talk about the construction issues on the next webinar, but it's paramount.
That's right. Really every installation of a TRM, whether it's on a channel, slope, backside or levee, whatever the application is, should have a trench around the perimeter. The trenches serve a couple functions, and we'll talk about it more in the next webinar. But really, it's to secure the material down and to minimize any water flowing below the material itself.
That's right.
Next question. The presenter's full name, just so you know, it's Dr. Chris Thornton. He's a professor at University of Colorado State University. Next question. Any testing for secondary rooting from larger plants outside the actual channel slope area? We've done a various amount of tests on different vegetation types. Anywhere from unvegetated, 16% vegetated, 30%, 70%, sodded, seeded, different types of seed. I don't know if we've done any on more robust vegetation types like small shrubs or trees, if that's what you're asking. Chris, do you have any experience with those?
No, everything has been more of the deciduous vegetation, grasses, but I haven't evaluated other types of vegetation.
The next question was sort of along the same lines, different types of seed mixes. I know we've done some Bahia, Bermuda, fescue, Kentucky bluegrass, California brome. Any other ones that stand out that you can think of offhand, Chris?
No, those are the Bahia and Bermuda, Kentucky. Yep.
The next question, I guess, Chris, you can maybe answer this offline per your last comment. Have you tested HydroTurf? I'll answer this. He has, but he can talk about that to you later.
Yeah. Yep.
Next question is, how does growing seasons affect the effectiveness of TRMs?
Well, that's where it all comes back together, right? Is understanding the geographic location that you're in, the type of vegetation that is native to that. We can't get Bermuda grass essentially to grow in Colorado, right? We just don't get enough water. So we have to have an understanding of what we're tending towards. What can the environment produce vegetation-wise, and then by adding a TRM to it, how much can we enhance that? So the whole thing with the Beasley number is having an idea of where that target, where that natural Beasley number is in the system that we're working in, and then that's the value that we're going to be able to achieve with the enhanced stability then of the TRM.
Okay. This next one's sort of similar in terms of trying to interpolate between tests. The question is, can you use the results for other grass types, other types of grass or weeds? He says not familiar with the topic, so I guess trying to understand if with the testing we have, can you use those results for other types of vegetation?
I certainly think you can, but that would be a case-by-case evaluation so that you understood again what types of vegetation and densities and growth conditions you would have at the site, and then what can we correlate that back to the body of knowledge that we have from testing and interpretation.
Okay. The next question, it says, you didn't talk much about testing of the combination of stone and TRMs. Will that be in a future webinar?
No, really, just because there's a lot of stone work that's been done, stone testing that's been done. So it's sort of like I said with a toolbox. You take the stone tool out when you need it, and then put it away and bring the TRM tool out when you're ready to use it. So I wouldn't say that you need to test them in conjunction with each other, but they need to be designed in conjunction with each other with the appropriate methodology for each technique.
Right. So understand each of them separately and how they're performing, and then make sure they integrate well.
And then integrate them, which is the constructability. That's an important piece, is to have that interface between techniques detailed very well for the contractor.
Great. Next question is there any testing on desert Southwest native species?
Not that I'm aware of.
I would say, I don't know about laboratory testing, but we do have a lot of installations in the Southwest that have been tested over the past 20 years, some of them. And several years ago, we did sort of a post-mortem evaluation on these projects with a engineering firm to go back and either recreate the hydraulic events and determine actual shears and velocities, or just determine the shears and velocities based on watermarks, and sort of understand what really happens in these channels with the TRM and native vegetation. So we do have a lot of good information on real-world performance in the field, and we can share some of that with you if you have more questions. Next question is sodding the best way to vegetate, or is hydroseeding better?
I wouldn't say it's better. I would say that if you need the belt and suspenders of having vegetation quickly, then sodding's a better way to go. Hydroseeding, I think, has the potential to provide that a greater initial protection than just seed. But again, depending on the location, geographic location, as to how fast that vegetation would establish, I think it might sort of be a wash. So I would look at the economics of that.
Yeah, a lot of times, depending on where you're at, whether in Oklahoma or Louisiana or Florida, sod can be pretty readily available and pretty economical. Other places, it just depends.
Right.
The next question, and I might need some clarification on this one. It says, are you getting any piping along the boundary between growth media topsoil and the lime stabilized base?
We haven't ever tested a stratified section like that. The lime stabilized tests that we did were just lime stabilized clay in the tray, just like the bare clay, or just like the unreinforced sod. So we didn't have a condition where we had lime stabilized clay and then vegetation on top of it, because actually vegetation doesn't grow in lime stabilized clay very well. So you'd have a slip plane. So even when we first looked at this a number of years ago, evaluated the lime stabilized clay, it was under the understanding that it wouldn't be vegetated, that veg wouldn't grow there, but the lime stabilized clay would be the final surface. And It didn't perform well.
And last question is, have soil crusts been evaluated?
Soil crusts?
Correct.
No, not to my knowledge.
Okay.
I'm assuming that means like after a fire or something.
I'm not sure.
Yeah.
So that is the last question. If you guys have any other questions or clarifying questions, biological soil crusts. Thank you.
Yeah. To my knowledge, no.
Okay.
I have not been part of any of evaluating those.
Well, Chris, thank you for helping answer the questions. Thanks for a great presentation. And thank you guys for your participation as well and questions. If you have any further questions, you can reach out. Happy to help in any way we can.
Yeah, if I can answer anything, let me know. Appreciate the opportunity, folks.
And we will have a part 2 to the webinar. We talked mainly about hydraulics and hydraulic testing and the connection with some index properties today. The next webinar will be on Friday, December 13th at 1 o'clock Eastern, and we'll focus on the non-hydraulics, everything else, whether it's durability, installation procedures, design process, really look at everything that encompasses the rest of the use of these materials for proper application. Hope you guys join us for that. Thank you guys for your time.
You there, Drew?